This is IAQ Radio, Indoor Air Quality Radio, the voice of the indoor air quality industry, with your hosts, Radio Joe Hughes and the Z-Man, Cliff Zlotnick. And now, Radio Joe Hughes.
Good day and welcome to IAQ Radio Plus, episode 691. And this week we welcome back Concrete Bob Higgins to wrap up our Moisture Bob series. We're going to do a final show on concrete moisture inspection, the fundamentals, kind of take all the information from the series of shows we've done and try and break it down into some practical things people can do in the field. After a series of these shows, it looks like it'll be a good way to wrap things up. But before we get started, we have to thank our sponsors. They're the reason we can continue doing the show. And don't forget about afterthoughts.iaqradio.com, sponsored by First On Site. Our marquee sponsor is First On Site at firstonsite.com. Our association sponsors are the American Conference of Governmental Industrial Hygienists, ACGIH.org, the American Industrial Hygiene Association, AIHA.org, the Institute for Inspection, Cleaning, and Restoration Certification, IICRC.org. Industry sponsors are AEML Laboratories, AEMLINC.com, Particles Plus, ParticlesPlus.com, TSI Inc., TSI.com, Tramex at TramexMeters.com, Healthy Indoors Magazine, HealthyIndoors.com.
And now you can win a cool prize. It's time for the IAQ Radio Trivia question. Be the first to correctly answer. Simply email your answer to czlotnick at cs.com. Or if listening live, just text your answer from your computer. And now, here's the Z-Man.
Hello, everyone. Congratulations go out to Dawn Weeks, Ottawa, Ontario, Canada, who was first to identify Nikola Tesla as the holder of a patent for a device to provide a simple, cheap, and effective apparatus for the production of ozone or such gases as are obtained by the action of high-tension electrical discharges. The IQ Radio Trivia question for today, February 24, 2023, has been sponsored by TSI Inc., an industry leader in precision instrumentation for monitoring of indoor air. Learn how to expand your IAQ investigations at TSI.com. Here's today's IAQ Radio Trivia question. Name the term that is defined as follows: a destructive condition caused when ground moisture rises into and up a masonry wall via capillary action. Back to you, Joe.
All right, thank you, Cliff. I also want to mention, welcome back the Restoration Industry Association as an IAQ Radio Association sponsor, and of course, Tramex. We appreciate them both joining us and joining the family of sponsors. Bob Higgins has been involved with moisture-related issues in concrete and waterproofing since 1976, and he's been developing products for such use since 1980. He was a product development chemist for SINAK. He has expertise in moisture-related concrete issues, having been involved with waterproofing, technical committees, professional groups, lecturing, teaching, and construction defect litigation. Welcome back, Bob.
Thank you, Joe. It's great to be back.
Great to have you.
Thank you.
Hey, I was kind of hoping let's go back to the basics, the fundamentals here, and because I started to get a little confused with some of the things on some of the earlier shows with respect to how moisture moves in concrete. So let's start with the phases of water. I mean, I think everybody knows we got, liquid, vapor phase, solid phase, and then there's also water that's being adsorbed or absorbed. Sometimes they call that bound water. I wonder if you could add anything to that.
Actually, I'm glad you brought all that up, because everybody is taught about the three basic phases of water, and that's in an unrestrained environment, which is your gas, which is water vapor, humidity. Then you have liquid water, then you have ice, which is your solid. But in an absorbed form, water behaves completely different. And that has not been used in many of the studies. In fact, almost none of them that I've seen. And I'm glad you brought up bound water, because sometimes bound water is misinterpreted. True bound water, for example, with concrete, is part of its structure. The only thing you can do to separate it is use an extraordinary amount of heat to flash all the water off. That's truly bound water. Now you can have bound water, for example, if it's ice, it's temporarily bound, but that's just a temperature situation. And it's like when you have capillarity, you can have bound water in them, but there's a ebb and flow to that as well. So it's not truly what I would consider bound water. It's still dynamic. And if it's dynamic and will change in a normal environment, I don't think that we should call that bound water. That is adsorbed and absorbed water. And that can behave so much different because water tends to go from warm to cool. That's the way it moves. But then all of a sudden we'll see these things such as capillary action and some of these other movements with moisture that seem to defy the physics that we've been taught. And it does in a way, only because the chemical reaction where the water's cohesiveness, its ability to attract itself and stick together, is actually overcome by the attraction of whatever it's sticking to, which is the adsorb. But then there's salts and there's other materials that will absorb water. And then once again, that behaves in a different manner than adsorbed water. Now, this is really complicated, and that is the crux of the issue. And that's where we need to get to the basics. Testing moisture is not complicated. Unfortunately, the industry has made it look and sound complicated, but it's not. It's really simple. It's either there or it isn't. And what are you measuring? And the different types of devices, most of them are very accurate, irrespective of what the different marketing people say. Well, this is defective because of this. They're not defective. They just measure something that isn't as important as maybe something else, or isn't as contributory as to what you're really looking for. And that's the biggest problem. Now, the complications in concrete are very complex. And the industry, for whatever reasons, made it sound real simple that concrete's a sponge, it sucks up water, and this is what it does. It's not that simple. So what we need to do is we need to get back to the basics where moisture testing is simple. You can do it. Just about anybody can learn to do it and interpret the data very accurately. And it's not really necessary that you understand all the complexities in concrete, because if you're testing for moisture, test for moisture. You're not testing for everything else. Why people want to take on the expert mantle and something like that, where they want to become a concrete expert, I would highly recommend you don't do that. Because here I am, I'm nearing 70 years old, and I feel like I don't know squat.
I understand that. And believe me, after these 4 or 5 shows, I'm starting to question my own knowledge about these things, Bob. But let's go first back to some basics. How does moisture move through concrete, or does it move through concrete? What are the major mechanisms of moisture moving through materials?
I'm so glad you brought that up, because when the flooring industry has been taught that moisture moves from the bottom up through the top and then starts destroying your floor, that is a bunch of nonsense. That violates the laws of thermodynamics and physics. It does not do that. What happens is they're confusing diffusion with moisture migration. Now, diffusion is really easy to understand. If you have a container, even whether it's concrete or semi-porous, semi-permeable, whatever, whenever you have a container and you add something to it that isn't in the rest of the container, it tends to diffuse and wants to migrate and moves through. So even if the water itself isn't migrating, the material that's being transported is using the water as a vehicle for transport. So if you have 2 containers, and I learned this in school, you have 2 containers and they're separated by a valve and a connector. Well, one has dye in, the other one's clear. Well, you open up the valve and the dye starts to move, and slowly moves until it equalizes. Well, the water didn't move. So that's being misinterpreted as moisture migration. That is not moisture migration. That is transport of soluble materials. That's what we're seeing, and it's been misconstrued for decades. And by having this bad information, we keep piling other bad information on top of it, to where in the last 20 years, moisture claims in floors have tripled. It's now over 3 billion a year. That's ridiculous. It should be just a nuisance item rather than a major issue the way it is.
And later, we're going to get your thoughts on how to stop that $3 billion problem. But before we go into that, let's talk a little bit about capillary action, capillary suction. I've heard it defined as diffusion. First, capillary suction. I was going through some old shows and some documents, and I came across Bill Rose's book here, Moisture in Buildings. I think it's, or Water in Buildings, he calls it. And there's a section on the rising damp. And this kind of helped me better visualize your thoughts on the topic, because, you know, I get some pushback that people say, well, capillary suction, that, you know, you can see water move from the base of a tree up to the leaves, and that the same thing happens in concrete, and that we're wrong on that. But I was reading through Bill's book, and it said those familiar with the problem of rising damp also know that rising damp is a problem much more in cold buildings than in heated buildings. In fact, one can sometimes determine whether or not a building is heated by the amount of capillary rise. So he's saying there is capillary rise, but it's much more prevalent in cold buildings. And that kind of made me think of what you're talking about when you say that it's defying the laws of physics for moisture to move from cold to warm. Can you comment on that?
Yeah. I've been involved with a lot of restoration. I did some historical restoration over in England, for example, with some of the buildings over in Bath, England, and over in Derby. And they said, well, we're having rising damp over here. I said, of course, because that's the cold portion of the building. It doesn't get a lot of sun. And they looked at, for all the years that they've been looking at that, they didn't realize that the sunny side of the building had almost no damage, but the cool side of the building had a lot of damage, where it was covered with trees and was constantly shielded from the sun, because moisture moves to the cool side. If you keep those basics going, capillarity is not a mystery. But one of the things about capillarity, where it can travel, is with some of the different types of salts, is some of these salts become more chemically active as they get warmer. So it will seem like that's a capillary draw, that technically that's not a capillary draw, that's a chemical attraction of the salt to the water. Because like Dr. Joe said at the Building Science Conference, that that moisture moves to the cool side. It doesn't move to the warm side. I said, well, what's the transport mechanism? He said, there isn't one. He said, it is diffusion. So I came out of there even more confident than I went before, because all this information that I've been putting together for the last few years is accurate. And you can test for this, and you can anticipate it. Because a really good example of water moving to the cool side was, if you go on the internet, they have these basketball courts, and some of them, if they don't if they don't turn the HVAC system on soon enough, here's a good example. This one, this was I think it was I forgot who the teams were, because I don't know.
Minnesota.
It's like the Minnesota Timberwolves.
Well, anyway, as people were walking into the building, they hadn't turned on the HVAC system, and the floor was very cold. So the more people that came in, the more moisture was being added to the environment. So what happened is, started sweating, and the players started slipping and tripping. So they tried to mop up the water, and every time they mop up the water, they put blowers on it. It just kept coming back and kept coming back. They finally had to cancel the game. And this it's simply because moisture originated from the ambient conditions. And this is really common, and this is the primary moisture source for virtually all concrete floor surfaces. Because if you think about it, The air temperature is typically averages warmer than the concrete surface. The concrete surface averages warmer than the concrete underside. So the movement is down from warm to cool. So how this magical mystery of moisture migrating up from the ground level, that's ridiculous. It doesn't make any sense. But we've been led to believe that. We've had a suspension of belief and suspension of belief in science and physics to chase these stories that keep people busy because people are confused, because they can't get to a conclusion if you don't have the right data. You can't do it.
Hey, Bob.
Cliff, let me let you jump in here.
Yeah, no. Okay. Before you mentioned the salts a couple minutes ago, about 2 minutes ago, you were talking about the salts and so on and so forth. Can you tell the listeners where the salts come from? Do they come from the ground? Or does the water dissolve the concrete and they come from the concrete? Where do the salts come from?
Great question.
Really good question. Most of the salts that we're concerned with originate in the concrete, and they develop over a period of time, and they move around, they reorganize. Now, what this is called, and I have not seen this in any study, anytime, anywhere, and it really irritates me because this is an established fact. When you have salts, they will have what's called an ionic dew point. Now, everybody thinks dew point is atmospheric, that it has to get to 100% relative humidity. That is not true. Ionic dew point is really easy to demonstrate. You can take a surface and you sprinkle table salt on it, for example. Now, if the relative humidity in the room is like 60, 65, 70%, it's dry. However, if the relative humidity in the room climbs to 80% or higher, all of a sudden the surface gets damp because the salt has attracted moisture from the air. That is called ionic dew point. And the different salts in concrete, depending on the congregation and how concentrated they get, they can actually begin to pull water from the air at relative humidity of less than 9%. So you can actually have liquid water, even if the relative humidity in an area is 20%, you can still have liquid water. And here's the other screwy thing that it does. If these salts concentrate, they start changing the behavior of the water. For example, if you have a 20% sodium hydroxide solution, which is the most common alkaline material in concrete, if you have a 20% concentration, what it'll do is it'll lower the freeze point of water to about minus 13 degrees. Now, if you double it and goes up to 40%, believe it or not, the freeze point of that water solution is 59 degrees Fahrenheit. The water is behaving like it's frozen, like it's a solid. It does not behave as a liquid anymore. It does not want to go into a gas. You've now changed all the rules simply because you added an element to it that is not an unrestrained environment. These are not being considered when you're doing your testing. So when they're running relative humidity tests, say, well, gee, this Tramex meter must be wrong because it says 5% and we're getting a 75% relative humidity. Well, that's a really scary piece of concrete because if it's 75% relative humidity in the concrete, that means the alkalinity concentration is very high. And it's going to be damaging to adhesives and anything else you put on the floor. But everybody's focused in on moisture as a relative humidity and some of these other nonsensical measurements they use. Relative humidity is really good if used as a forensic tool, but it is not good. In fact, it's misleading if you use it as a device to measure moisture content in concrete. It does not do that.
Well, okay, so I'm going to kind of switch gears a little bit because I've got a text question from a listener here, and I think this may be a good time to look at. So based on what you're saying, what's the keys to help drying concrete? I mean, a lot of our audience are restoration contractors that come in after a flood or, pipe breaks or whatever the case may be, the concrete's wet. What are the key points you would try to get through to them with respect to actually drying that concrete?
Again, that's a great question. For the restoration contractors, they get really confused because sometimes they'll start drying out the concrete. They have this steep drying curve, all of a sudden flattens out. Once it flattens out, that's as dry as that particular concrete is going to get, and don't try to over dry it. That's my biggest form of advice. And then once you get to a point where you're somewhat stable, just keep the air movement. And then once you put a coating on, that's where it's going to stay. But if you stop air movement, especially concrete, and I'm just talking about concrete, will begin to actively absorb the moisture again. You want to keep it moving. The dead air is your biggest enemy when you're dealing with concrete.
And what about the ambient, the conditions in that, normally we're in a building of some kind. Should we also control the temperature and the relative humidity in that environment?
Yes, and the concrete will actively begin to, in fact, it's probably even more so if you want to go in absolute terms, but it seems like the critical number is staying at least 10 degrees above dew point. If you're within 10 degrees of dew point, the concrete will be actively absorbing moisture, especially with those salts. Remember the ionic dew point. It will start pulling in moisture and absorbing moisture even when you don't think it's supposed to be doing that. But if you understand the basics, that is not a mystery anymore. But we're not being taught the basics.
And I see these, drying chambers set up where they're trying to, they'll cut the room in half and heat the area underneath the drying chamber next to the concrete. Does that make sense to you?
Yes, it does. It does make sense, but I would not overheat it and I would not over dry it. What you want to do is Mickey Lee brought up some really good points, and he's got some excellent information where you want a steady rate of drying as much as possible. You don't want to try to over dry it, because what will happen, you can actually get blocking. For example, if you over dry, it's like when you heat up concrete. If you get an area where the alkaline starts getting concentrated, it won't allow any evaporation. It'll just stop. So unless you're drying it, at 5 and 10% relative humidity, you're not going to pull any more water out of that concrete, especially if you accelerate too quickly. The worst thing you can do is concentrate the alkalinity. That prevents drying.
Okay. What about using desiccant air and tenting? I mean, we talked about tenting and heat, but what about using desiccant dehumidifiers and tenting?
Theoretically, that's a great idea, but you have to understand that the desiccant isn't as efficient or as effective as the desiccant that's already in the concrete. There's very few desiccants that are more robust than sodium hydroxide. Sodium hydroxide has a critical, and that's one of the things I'd like the restoration contractors to really get up to snuff with, is go look at the critical humidity threshold of whatever desiccant you're using, and then compare it against sodium hydroxide and the calcium hydroxide, which are the desiccants in the concrete. Those are your primary dessiccants. So where do
they come from?
The calcium hydroxide comes from development of cement. That's a byproduct of cement formation. The sodium hydroxide is just a byproduct that's in all concretes, and it's in some parts of the cement, and even more so now, because that's another subject we can explore a little bit, get a little deeper with. But sodium hydroxide has become significantly worse, and started right around 2002, and it moved through 2019 to where now the concrete we're dealing with from 2019 onward, and there's that muddy area in between 2002 and 2019, where this concrete we're dealing with now, the old rules no longer apply, because it behaves in a completely different manner, because there's more alkalinity in it, and that alkalinity is sodium hydroxide.
And this is from the grinding of the cement that was required by EPA, or no, wait, that's a little different topic there, right?
Yeah. Well, those is grinding aids, but but it is tied in with that, because the EPA requirements had them recycle what's called cement kiln dust back into the cementing process, and that's now in our cement. Well, that is a lot more alkaline than it used to be, and it behaves differently. So we can get into those really weird reactions that sodium hydroxide does to water, or makes it bounce around. Because if you look at the freezing response that water has when you go into the different solutions and concentrations of sodium hydroxide, it looks like a drunken mosquito. I mean, it goes up and down and then all of a sudden it just takes off. Where technically speaking, you can actually get over 100 degrees Fahrenheit in the water. If the alkaline is high enough, the water's still frozen.
Well, all right. Now, again, I'm going back to the practical side. We've got these guys out there trying to dry concrete. We've got these dates that you mentioned, from the 2000 until here most recently 2019. What would you recommend they do differently with an older concrete that maybe was poured in, 1920 compared to one that was poured in 2005 or one that was poured in 2022?
I recommend the approach remain the same, but your evaluation has to be somewhat flexible, because with older concrete, it changes chemically inside. There's this process that they've assigned to it. It's called concrete hysteresis, where the difference between ingress and egress of concrete varies over time, and where the ingress is a lot more robust than the egress. So what will happen if you're trying to dry out older concrete and you get a bunch of this collection of alkaline up towards the surface, it's going to be extremely difficult to dry. And you'll be wondering why you can't put a floor down because it stays wet. Well, it's full of salty water. You can't dry it out. You probably have to remove it. You probably have to skim, scratch down and grind into the concrete or shot blast it and get rid of that layer.
How far?
Depends on the concrete. What I would do is I would probably grind down and use a Tremex meter, because as soon as you watch it drop, then you know you're safe.
That's the other question.
Yeah.
How do you know when you're over drying? How do you calculate when you're over drying something?
When you're paying attention to what you're how much moisture you're extracting, when you start getting where you get a slope, where you go from a sharp slope down to where it starts flattening out, stop.
But
That's
continue air movement.
Correct.
But continue the air movement, continue to make sure the environmental conditions are normal. So don't turn off the heat altogether, or don't let it get too cold.
And then you want to coat the concrete before you turn it off, because you don't want to trap the ambient moisture back into the concrete. What you want to do is you want to isolate the concrete from the ambient conditions.
Great. Excellent. Okay, and I've got another text here. There's a local trend in their area where builders are using granite dust instead of wash stone under slab on grade because of the cost savings in new homes. I'm having trouble seeing. Then they throw down a vapor diffusion barrier and pour the concrete. It appears the granite dust holds a lot of water compared to rock or sand. Does this produce a risk of capillary suction?
What I don't like is the trend that the concrete industry went to, where they used to put the vapor barrier down, they put the gravel layer on. That's a capillary break. And if you don't grade the stone correctly, it's not going to be a very good capillary break. So you have to make sure it's well-graded stone. I do not like vapor barriers up against the concrete. We were told and taught for decades not to do that, because the concrete surface dries out disproportionate to the bottom side of the concrete. Now we're getting all these curling slabs and micro-checking on the surface. That to me is one of the dumbest things we ever did, but that also lets me know that most people in the concrete industry have knowledge by rote rather than knowledge of practicality. The practicality is, so what if there's moisture underneath the concrete? If it moves from warm to cool, it's not going to go anywhere. Who cares? So look at the moisture can get in. So what? The bottom part of the concrete has its own gradient. The sides have its own gradient. The top has its own gradient. Where it really got dramatic to me was there's this 1974 study by the Army Corps of Engineers where they were testing concrete and its response and drying it out, and all the conditions that may go on with the concrete is exposed in a nuclear facility. Well, they exposed the concrete to 150, 160 degrees, but when it got into a certain point, the moisture content during the entire duration of the test never changed. It didn't move. Why? The dynamics that we're talking about. But they didn't explore it. They just, Everybody abandons the chemical reactions that are going on. And if we'd stop doing that, we would figure this out, which is why I like when you do a simple test. You test for moisture, but you have to test for moisture. If you want it to be accurate, it has to agree with a gravimetric. Gravimetric gives you an absolute number of non-bound moisture.
Bob, I want to go into that in more detail, but first I got a break for halftime. Thank our sponsors. I did not get a chance to put the Restoration Industry Association in the mix here, but we want to welcome them back and thank the rest of our sponsors, John. Our marquee sponsor is First On Site, your trusted full-service disaster recovery and property restoration company at firstonsite.com. Association sponsors are ACGIH, advancing careers of professionals in environmental health, industrial hygiene, and safety, interested in defining their science. ACGIH.org. AIHA, healthy workplaces, a healthier world. AIHA.org. The IICRC, a nonprofit standards development and certifying body for the cleaning and restoration industry. IICRC.org. Industry sponsors are AEML Laboratories. Free shipping, great pricing, same-day results with no rush fee, AEMLINC.com. Particles Plus, feature-rich particle counters and air quality instrumentation. Count on us, particlesplus.com. TSI Inc., an industry leader in precision instrumentation for monitoring indoor air. Learn how to expand your IAQ investigations, TSI.com. Tramex Meters, developing modern dynamic moisture meters and humidity monitoring systems since 1974. TramexMeters.com. And Healthy Indoors Magazine, a free online magazine for industry professionals and consumers. HealthyIndoors.com. Okay, we're back with Concrete Bob Higgins here. Concrete Bob. I kind of want to get into the inspection side a little bit here. And I've had a couple text questions that I think we're going to answer over the next 10, 15 minutes or so here. But one of the things that people commonly are asked to do is figure out why certain things are wet or moist or whatever. And one of the ones I've seen commonly is you've got some mats in a gym or in a wrestling room on a concrete floor, and they get wet underneath. There's moisture. They start to get mold growth. How would you go about evaluating what moisture problem caused that?
First and foremost, I would recommend, if possible, find out what the concrete mix design is. Find out what the original mix design is. And if that can't be found, then I would recommend doing a Tramex meter test. And then if it is elevated temperature or elevated moisture content, depending on the finish of the concrete, you may want to scarify the top portion of the concrete. Now, what I tell people to use as a rule of thumb when they're scarifying concrete, to make sure you're down past anything that's occluding the surface or covering the surface or interfering with the free passage of moisture in concrete, you have to make sure that you do a pH test, and you really want the pH test to be at least between 9 and 10. If it's lower than 9, you're not testing concrete yet. You're testing whatever dirt or whatever coating you have on there. You got to remove it. It's got to be at least between 9 and 10, because fully carbonated concrete is right about 9.5 or so. That's fully carbonated concrete. Now, I have people say 9.45, but I don't know that that's technically accurate, because I won't go into that, but you can't really test calcium carbonate. You test what it becomes if you get it wet long enough, and it turns into calcium bicarbonate. But so you're not actually testing that, but you are testing concrete that's exposed now rather than something else.
Now, maybe I'm wrong. Let's go back up. Would I first not want to look at the environmental conditions in that area and see if maybe the mats are causing a dew point problem underneath them?
Yeah, and that's why I started using this kit where I would use an infrared thermometer. I used a digital hygrometer, which would measure the temperature of the air and the relative humidity of the air, then put the Tremex meter down there. Between all that collection of data, and if it's a multi-story building, I would also use infrared to find out how much potential stack effect you have. And more times than not, you just have a really cold surface. It's out of balance with the remainder of the building. So if you have a gym floor and people are in there breathing and sweating and the room gets hot, well, yeah, it's going to get wet.
Yeah, and they're typically on the ground floor or in a basement somewhere. Anyway.
Exactly. Where's the water going to go? It goes into the concrete. You are feeding sweat right from the ambient conditions.
So we figured out that maybe it's not that's not the problem, that maybe it's something else, or let's go to a different type of inspection where we've actually had well, let me start with this, the meter. You mentioned Tramex meters, and I know there's a bunch of different meters out there. Tramex is a sponsor. We appreciate that, but why do you seem focused so much on their meter versus other meters?
I'm a bit of a curmudgeon. And I'm notorious for that. If somebody tells me this is what it does, well, you better prove it to me. And then if I am interested in it, then the next thing I do is I try to find out everything wrong with it. So when I was doing some research to find out the veracity of Tremex, I came across this finished test by VTT, which is they're a massive, well-respected testing agency in Finland, and they tested different moisture devices in the lab, and they compared it using a gravimetric, which that's my choice of baseline, because that baseline is it. But what they decided to do based on their lab studies, they went out into the field and they started doing the same thing. Everything changed when they went in the field. All these devices, even the calcium carbide and all the relative humidity tests, they just started moving all over the map, because as the concrete starts changing, whatever they're measuring, which isn't in a controlled lab environment where the temperature of the concrete on the top and the bottom and the relative humidity, everything's the same. Now all this dynamic is going on. Tremex was the only one that kept in alignment with the gravimetric. I said, oh my God, I just hit the holy grail here. So I'm sorry, I can't recommend something else until they've proven that's what they can do. If you can prove it in the field like that from a disinterested, accredited third party, now I'll believe you. But until it's done, no.
And this is a specific type of meter, right? It's a non-invasive Tramex meter, and these are designed for concrete?
Specifically for concrete. Don't use their other meters for concrete. You're going to get really strange readings.
Whoa. Okay. So
go ahead, Cliff.
Joe, when you talk about non-invasive, if I'm not mistaken, when we're using the meter on concrete, we are oftentimes invading the concrete, correct, Bob? We're drilling the holes and so on and so forth.
Yeah, I'm not a believer in that. I'm not a believer in drilling holes. But now, if you want to figure out what's going on inside the concrete, that's fine if you're doing a forensic evaluation. But most inspectors just want to know that this is safe for installing a coating or a flooring. Everybody's put all this complex bullshit in there for this testing. Really, all you need to do is just make sure that the moisture levels are down to a certain point that where the adhesive of choice can tolerate this environment until it sets and cures. And I've been told all this stuff about the moisture sensitive adhesives. That's nonsense. I have taken many different manufacturers. I won't name them all, but I've taken at least 5 or 6 different manufacturers. I've laid their adhesives up on the cement board, let it cure and set. I've stuck them in these buckets for over a year and nothing happened. So tell me how these are moisture sensitive. As long as they can set and cure, they're fine. Now, if there's a concrete issue, which comes up later on, it will start to deteriorate the adhesive or damage the floor. That's how you separate moisture issue from concrete issue. it's a concrete issue, there's nothing you can do about it. You need to bring in a concrete expert. But people are trying to cross over, and you do this obligation by estoppel, because now you're assuming you're taking on the mantle of the expert when you don't even know what you're testing.
Let me clarify too, Bob. We're also at times looking to see if there's enough moisture for potential of mold growth on, carpeting or other things that are next to the flooring. And you would still use the same procedure?
Correct. And I would do a site evaluation, and a site evaluation is the most important at time of installation. I really don't care what you do for testing, because all you're doing is you're just qualifying the substrate and the conditions. But the thing is, if people start walking in and out, opening doors and closing doors and windows and all that stuff's going on, everything's going to change after you've tested. Because I was asked in the seminar, they said, well, how much is it going to change? What's the moisture going to do? I said, well, it's going to do one of three things. It's going to get worse, get better, or stay the same. Pick one. I don't know what it is.
So you're recommending the Tramex meter, and others may use another type of, non-invasive type of meter. And these are reading down do they all read about 3/4 of an inch down into the concrete?
Yes. And again, I'm glad you brought that up. All the studies I've seen, now that the studies have gotten more sophisticated, the important area of the concrete is the top 3/4 to 1 inch of the concrete. The rest of it has almost nothing to do with the damage that we see on the surface. Because what's happening, especially with this more alkaline concrete, what they found is, and I can't go into, I don't want to go into the full thing because it's really complex, but what happens in the initial curing stage of the concrete for the first 2 to 3 weeks, the relative humidity in the surface of the concrete can actually drop down to 50 to 60%. That's happened globally. I saw that in Texas. I saw that in Portugal. I saw that over in the Middle East, over in Japan. They're getting very similar results. Now they know to look for it. Well, prior to that, everybody, me included, have always assumed that the relative humidity was high enough to produce cement. The relative humidity in that area and throughout the concrete needs to be above 80% to produce cement. If it drops below that, the cement doesn't form. Now you got a permeable, porous, garbage surface. So, and then Dr. Zollinger, who works with the Texas Transportation Institute, he decided to look at that a little bit closer. So he took some lab samples, and not in the field, but lab samples. And what was really dramatic to me was after a 7-day water cure, he sliced the top inch of the concrete off and had a compression value. It was 20% weaker than the remainder of the concrete. Showing once again the gradient portion of the concrete. It's the top inch. Now, here's where we're really screwing up with the flooring industry. You drill in 2 inches, well, you just bypass the problem area. You're not even measuring where the problem is. It's just nonsensical to me that how everybody gets so misled with this garbage junk science.
I think most of our audience,
there we go.
Maybe some will do the, relative humidity probes and so on and so forth. I think most of them just use a moisture meter, and they typically are dealing with concrete that has not been newly poured. It's been around for a long time. Now, we have some flooring inspectors as well that may be there for an inspection just after the pouring, but most of the time this is something that happened well after, or they're having a problem with, like I said, mold or something else, and they go around and they check different areas in the building, check the concrete, usually with a non-invasive meter, different product, different types, and they will oftentimes, at least in my experience, Bob, I'll find different areas will have elevated moisture content and other areas don't. And that doesn't seem to make sense if it's coming from from the air. But maybe I'm wrong on that. Can you kind of help me with that? And how many areas do I need to check? How many tests do I need to take with my moisture meter in a typical area? Let's say, I've got a 2,000 square foot home and I'm dealing with a slab on grade.
I don't know how many tests you need to conduct, but what I do, I test your perimeter areas. I check anywhere there's a difference in flooring material applied, because what's going to happen is the different flooring materials can get warmer and cooler where they have a different dynamic, and that you can start will produce like a mini gradient. The reason why I wanted to point out the 3/4 of an inch to 1 inch of the concrete surface, no matter how old the concrete is, that surface remains. Now it's more permeable, it's more porous, and any moisture that can get in there and any kind of environmental contaminant will embed itself in the concrete. You've got an eager, greedy mouth gobbling up everything it can, and then you're wondering why you have mold and mildew towards the surface. Well, it's, if you look at, if you dust your furniture once a week and you come up and you see all this on your fingers, well, that's all getting in there. It'll find its way in. Unless it's completely shut off and isolated from the environment, you're going to get this gradual buildup of contamination, especially towards the surface.
Bob, are there any meters? I've got a variety of floor coverings in my home. You got some laminate, you got some carpet, you got some, some slate tile. I've got different types of coverings on the flooring. Does that affect my moisture meter, and how?
It can, especially when you're dealing with something with lower or higher permeability. You're going to get differences. So, but whatever you're measuring is what it is. So, well, we need to remove this so we know what the moisture values are. Well, why? That's what's on there. That's what you're living with. Now, I understand that you need to remove that to find out what's going on with the concrete, but you also want to find out, get your baseline of what your existing conditions are. Now get your baseline by removing some of these and getting down to raw concrete. Now you've got a baseline comparative. People do not do enough baseline comparatives.
Okay. Now, I noticed you mentioned you would start, at least, I don't know if you said you would start, but you would do perimeter and then work your way in, I guess.
Yes.
And I'm wondering, is that in part because, as you said earlier, moisture can possibly come from below, it can come from the side, it can come from above. Is that in part because it might be coming from the side? Yes, because you can have a warm side of the building and you can get really dry, nice readings over there, and you get over to the sheltered side of the building where it's mostly under trees and everything else. You may get a spike in your moisture readings. You're mapping your environment. You're finding out what it is. So what you do on this side of the building is going to be a different approach than what you do this side of the building. But everybody wants this to be homogeneous, and let's just take a general approach. You really can't do that. And I'm wondering, from your experience, I used to go out and work with restoration guys and mold remediation contractors. They've got a variety of different types of meters. How important is it to have a meter made specifically to measure concrete? Let's just say that. Let's go with that. It's like wood species. And that's one of the things that really bothered me. And I brought it up at as some of the concrete conventions, and didn't go over very well, but it was pretty funny. I said, why are you evaluating these cementitious materials as though you were evaluating concrete? They do not evaluate wood species in the same manner. Each wood species has its own hygroscopic moisture value. Now, if you based everything on pine, it would damage the other floors that don't have the same hygroscopic value. It's the same thing with any cementitious product. If your concrete is changed in water cement ratio, or you got a cementitious underlayment, like some of these self-levelers, they're going to have a different moisture level than the concrete, and that's okay. It doesn't have to be the same. It has its own intrinsic hygroscopic moisture value.
Now, again, that's establishing a baseline. We're not very good in the concrete industry or the flooring industry at establishing baselines. They just don't do it.
I guess when we come back, what I want to do is give you a scenario, a typical water loss, and how you would measure and monitor when you first get there, how you would measure and determine the extent of the water damage to the concrete, or the extent of moisture in the concrete, and then also how to monitor during the drying and when we're done. But before we do, I want to go to the roundup and thank our roundup sponsors.
Okay.
Okay, the roundup. We're going to mention first our two new sponsors, the Restoration Industry Association returning, and of course, Tramex Moisture Meter and Detection. Cliff, before I get started, do you have any follow-ups you want to get in?
Yeah, I do have one, Bob. So let's just say that, before we get into this water, something more complicated. Let's just say we have a water loss and we have a normal basement, and we have the cement or concrete is exposed. It gets wet, and we want to dry it. So we put air movers on it, and so on and so forth. Why aren't we done? What can happen to that concrete if we're not going to put tile floor on it or anything else? Isn't it going to come into equilibrium itself if we don't coat it or put anything on it?
Yeah, it'll go into equilibrium if the environment's constant. It's more like it's dynamic equilibrium, and it's a relative equilibrium, because here's the funny thing with concrete. In the equilibrium, when it's being cured, you have this top 1 inch that's got a 50 to 60% relative humidity. Immediately below it's 90%. Why are those staying so different? Why such a switch? Because again, you're dealing with alkalinity concentration. It may actually have more water in that so-called dry layer than it does in the remainder of the concrete, especially since it's more porous and permeable. Concrete is an odd duck. And again, even if it goes into equilibrium, it doesn't mean you're not going to have a moisture problem. Because especially as it gets older, there's nothing scares me more than 30 and 40-year-old concrete, because I don't know what the hell I'm going to find. You have to go completely open-minded.
Let me ask you this. What about the fake faux stone they put on the exterior buildings? That's basically made out of concrete, isn't it? Or cement of some kind. It's just formed to look like stone. Would you use similar types of methods and techniques for inspecting that?
I'd have to look at it closer. I want to say yes, but being the skeptic that I am, I always have to evaluate what is its baseline, because I don't know what its baseline is, because I don't know what kind of polymers it has in it. Because some of these materials may have something like a material that holds onto water. It's got higher hygroscopicity than the native concrete. So it may have, say, it's perfectly okay at 8% moisture content, whereas concrete's considered dry at 4.5%. And they get along just fine. But I don't want to try to evaluate that using concrete itself as a baseline. I need to find out what that specific baseline is for that specific product. Because I don't know.
Let's say we've got a typical basement water damage scenario. We've got a hot water tank that breaks. People aren't home. They come home a couple weeks, or a couple days later, and they've got an inch of water in the basement. Obviously, first we're going to get the water out, but then how are we going to evaluate it and how are we going to dry it?
Again, I use when I would dry out. I was in this high-tech building in San Diego, and they were saying, "Look at the concrete's wet, and it did this, that, and the other thing." And I looked at I got the concrete specs and looked at that. I said, "It's not the concrete. It's a 0.45 water cement ratio, and the moisture levels you're claiming that are not possible. So I don't know what you're doing." So I used the Tramex meter and measured damp. I said, this is all ambient created. I said, how do you know that? I said, because when we walked in, I put the hygrometer down here. And as we were talking, the relative humidity in the room was at 52%. Now that we've been in here for about 20, 25 minutes, the relative humidity is up to 78%. Now we're within 10 degrees of dew point. That's where the moisture is coming from. I said, and then I put the hygrometer underneath the lid of the adhesive, and it just pinned, went well over 90%. I said, this is a water-based adhesive, isn't it? I said, yeah. I said, okay, now if we duplicate what they did, we're going to have the same problem. So we reenacted, they duplicated, sure enough, had the same problem. So now we're going to condition the space. We're going to dry it out, bring it down to my cutoff's 4.7%, but we got down to 4.7%. I said, now keep the air circulation going. You dry out the concrete because we had air blowing against the concrete. Since these were smaller rooms, we had to use dehumidifiers because there was no exhaust area. And when we brought it down, I said, okay, now keep the air movement going. They reinstalled the same floor. They did a bond test. They couldn't get the floor off. We took that and duplicated all the way through the project. Now, here's how important that project was. For the 12 rooms, each one of those rooms would have cost $1 million a day to shut down. Each one of them. So this was a very critical installation. Said, are you sure? I said, absolutely. Because nothing else makes any sense. It was all created by ambient conditions.
I've got a good text here. This is a pretty common scenario. You've got a slab on grade, similar to, I've got a home here with a slab on grade. And let's say you've got hardwood, real hardwood, or even engineered hardwood over top of a concrete slab on grade. How do I guess I would use a wood meter to check the moisture content in the wood, but how do I check the concrete to make sure it's been dried out properly after somebody's done restoration?
Well, is this with a wood floor still on top of it, or you haven't installed it yet?
Yeah, I think they're going to try and dry that floor in place. That's typically the first response, is to try and dry it in place so that, you save a lot of money on tear out and replacement. Can that be done? And how do I verify it's been done?
I would, again, I use a Tremex meter. I would do the testing. I would make sure it's at least 4.5% or lower for hardwood. But I'm really reluctant for people to install hardwood directly over concrete. Concrete wants to stay wet. It's in its most comfortable state being wet. You really need a vapor barrier between a really good adhesive, something to really grab on and really slow down the amount of moisture that can emit from the concrete for a successful hardwood. I just don't, they're intrinsically incompatible with each other. So the thing is, separate them. Don't let them see each other. That's your best.
For that separation, do you recommend a sealant of some type, or can we just use, 6 mil poly or something like that?
A lot of these adhesives are already waterproof, so I would just do a little bit of an investigation where you may have to put down the adhesive spread, and that's, I would just go from there, because I don't know enough about the modern adhesives to talk intelligently on it. Heck, I'm a concrete guy. What I know about adhesives, hardwood, you can write on a gnat's ass with a blunt crayon.
Can the pH of concrete be chemically remediated? That's an interesting question.
It can, but you don't want to. And also, I'm glad that was brought up too, because high pH and high alkalinity have very little to do with each other. Because you can have something that's has a high pH, but it may not be highly alkaline simply because it's not concentrated. High alkalinity means something's concentrated or buffered. See, I run into that all the time where those are used as interchangeable terms. Because I gave a seminar, this is back in the mid-90s, and these wool folks from New Zealand were there. They said, what about high pH cleaners damaging wool fabric. I said, well, I don't think that's as big of a deal as the concentration, because the concentration is actually what's going to cause the damage. Because if you concentrate alkalinity in concrete, you can actually dissolve the rock and stone in the concrete. That's called ASR. You will actually dissolve it. So it needs to concentrate. The pH alone won't do that. So they did a follow-up, and I will take a lot of credit for this. They did a follow-up. It's called the Wolf Safe study, and they found there was no difference between cleaners between 4.5 all the way up to 12, as long as it didn't get concentrated. But as soon as it got concentrated, once you got much past a pH of 10, as you started concentrating, there was almost a linear correlation between the concentration and the damage to the fabric.
Well, we're running out of time. I've got a couple. I think most of the questions that were asked, Clayton, thank you so much. Clayton Shaw, who's also a flooring inspector, was helping to answer some of those. That he was talking about using the Tramex ME5 is a non-invasive meter for wood moisture. The CME4, CME5, and CME X5 are designed for placement over concrete surfaces. So thank you, Clayton, for helping with that. I've got one more question. When should an inspector know they are in over their heads and need expert help?
It's concrete.
If it's concrete?
When they're in over their head is when they can't dry the concrete out. If they try to dry the concrete out, it doesn't want to dry, or else if they're doing forensically, this is where I like RH probes. If you take a Tramex meter and use an RH probe, what you want to do is you want to compare the numbers. It's kind of like, I like what Andrew says, where it's like sighting down a rifle where you get two marks going. So if it's got a low RH, what I call low is anything below 90%, but you don't want it below 80% unless it's really old concrete. If concrete's 20, 30 years old, I don't have a problem with it having an RH of 75%. I do have a problem with any concrete that's less than 5 years old with an RH less than 80. If it's less than 80, you're going to have a problem, because now you're dealing with high alkalinity. Because the RH, when it's in an alkaline environment, what governs the RH is the concentration, not the volume of water. If you notice, the volume of water has nothing to do with the RH. It has everything to do with the concentration. So if you stick an RH meter or a sensor probe in each one of these, the pure water, even if there's hardly any water in there, well, if you're only going off of RH, you think that has the most moisture in it. It doesn't. So what you want to do is you want to use a Tramex meter and so if it's if the RH is 90% and the Tramex meter is showing 4.5%, you have a really good piece of concrete. No worries. But if you have a high rate of moisture, say like 5.5%, and the RH is down around 75 to 80%, you have a significant problem. You're getting concentration of alkalinity. But if I say both low, good to go, and that's what you want to aim for. But if you have a high pH, high RH and a high Tramex reading, you may be in an unfixable position. So what I would do is I put fans and blowers on and dehumidifiers on that. If there's not much change after a couple hours, you're probably in over your head.
Time to bring in an expert, huh?
Betcha.
Bob, thank you so much. I've got a couple. I know I've got one person at least that would like to get your email so that they can maybe converse with you on a project. Would that be okay?
Yes, it would.
Absolutely. Yeah. All right. So this is Radio Joe Hughes saying thanks to this week's guest, Concrete Bob. I'm still sometimes, I don't know. I'm still trying to figure this out. Cliff, any final thoughts?
Nope. I think the conversation should continue on Afterthoughts. So
afterthoughts.iaqradio.com, and we'll continue the conversation. This is Radio Joe saying thanks to this week's guest, Concrete Bob Higgins, my co-host, the Z-Man, Cliff Zlotnick. John, you got to have faith.
Thanks, gentlemen. It was great as usual.
All right. I always appreciate it, Bob. Most importantly, our loyal audience and our great sponsors, we appreciate. Next week, John Lapotere. Long time since John's been around. We're going to get an update on, there's a bunch of mold inspection and moisture inspection and mold remediation standards, going through the update process or the writing process right now. And John's heavily involved with those, and he's going to help us kind of sort out what's coming and what's going. So we look forward to having him and everyone else back on next week's next episode of IAQ Radio Plus.
For IAQ Radio, I'm Spike Reel saying thanks for listening.